Pluto is a distant, stealthy, and unassuming planet that was once part of our solar system. However, recent unsettling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that the cold world might be on a potential collision course with Neptune. But how feasible is this? And what might be the results of such a massive event? Are we witnessing bafflingly large, erratic behavior, or is there something else to this looming, unending setback? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, continues to be a subject of study and fascination in the vast universe. Recent hypotheses from leading specialists suggest that Pluto's orbit is perilously close to Neptune's. Neil deGrasse Tyson, Michio Kaku, and their colleagues are sounding the alarm about a possible hazardous collision between these two celestial bodies, which could pose a massive risk to Earth. But how is such an event even possible? In contrast to any other planet in our solar system, Pluto's trip around the Sun takes a staggering 248 years to complete. Since its discovery in 1930, Pluto has completed only one full revolution. The fascination doesn't end there. Its orbit is particularly elliptical and veers far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, tilted 17 degrees from the ecliptic plane. This steep inclination and unpredictability add layers of complexity to its orbital behavior, making it one of the most intriguing orbits in the solar system. One of the most significant aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years during each orbit, Pluto moves closer to the Sun than Neptune, defying what we might expect based on their typical positions. This naturally raises the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets and the intricate mechanics of orbital resonance. Shortly after Pluto's discovery, astronomers began studying its distinct path. Unlike the relatively flat orbits of most planets, Pluto's steep inclination and irregular shape posed a mystery. Despite this, scientists discovered that Pluto's orbit is stable over long periods, thanks to the gravitational influence of other planets, particularly Neptune. A crucial concept in understanding Pluto's stability is the three-body problem, a complex gravitational interaction involving three celestial objects. Pluto, Neptune, and the Sun. Predicting their movements is like forecasting the paths of three magnets pulling on one another. In Pluto's case, this interaction helps maintain its orbit despite its chaotic appearance. Key terms such as libration, orbital precession, and VZK wobbling are essential to this phenomenon. Libration refers to the gravitational dance between Neptune and Pluto. When Pluto crosses Neptune's orbit, the two bodies are separated by at least 90 degrees, preventing collisions. Orbital precession describes Pluto's vertical movement relative to Neptune's orbit, which adds an extra layer of protection from potential impacts. Another critical concept is VZK wobbling, named after researchers Vladimir Kozai, Kai, and Zal, who studied the gravitational interactions between celestial bodies. This wobbling helps explain why Pluto's orbit remains stable despite its irregularities. It prevents Pluto from straying too far off course, ensuring that its path remains relatively predictable over long periods. Numerical simulations in the late 1980s revealed that Pluto's orbit, while stable, is also chaotic. Minor changes in its initial conditions, such as its position or speed, can lead to drastically different trajectories over centuries. Despite this sensitivity, long-term simulations have shown that Pluto's orbit remains stable for billions of years. This stability is partly due to gravitational interactions with Neptune, Jupiter, and Saturn. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance acts like a cosmic safety net, preventing collisions. Additionally, Jupiter's immense gravity helps keep Pluto on a steady path, with Saturn playing a supporting role. Together, these 3 planets work in harmony to ensure that Pluto continues to move safely through space without colliding with Neptune or being ejected from the solar system. Without these gravitational mechanisms, the solar system will be far more chaotic, with objects like Pluto potentially colliding with other planets or drifting into interstellar space. Understanding these forces is crucial, especially with ongoing discussions about the possibility of a future collision between Pluto and Neptune. Pluto's orbit demonstrates how even seemingly unstable celestial paths can achieve long-term balance through gravitational interactions and orbital resonance. This highlights the importance of continuous observation and study, as these phenomena offer valuable insights into the broader dynamics of the solar system. The concept of orbital chaos, the sensitivity of a celestial body's orbit to its initial conditions, is clearly illustrated in Pluto's case. Even small changes in its position or velocity can significantly alter its trajectory. Numerical simulations have been invaluable in modeling Pluto's motion and predicting how gravitational interactions with Neptune and other planets influence its orbit. In the late 1980s, these simulations revealed that despite Pluto's unusual features, such as asynchronous libration and orbital precession, its orbit remains stable over vast timescales, on the order of billions of years. This suggests that, although Pluto's orbit may appear chaotic in the short term, it follows a predictable pattern in the long term. Predicting celestial movements, especially for irregular orbits like Pluto's, presents a significant challenge due to the inherent unpredictability of these systems. While numerical models provide powerful tools for forecasting planetary motions, their accuracy depends heavily on precise initial conditions. Even small errors can lead to vastly different outcomes, highlighting the limits of our predictive abilities. Despite these challenges, studying Pluto's orbit offers valuable insights into the gravitational effects of giant planets and the broader mechanics of the solar system. It demonstrates how the presence and positioning of each planet can significantly influence the stability and trajectory of other celestial bodies. As recent findings by leading astrophysicists suggest, ongoing research into Pluto's orbit remains essential, not only to understand its long-term stability, but also to assess the potential risks posed by its interactions with other planets, including Neptune. This knowledge helps us better comprehend the dynamic nature of our solar system and our place within the vast, ever-changing universe. Although current models suggest that a Pluto-Neptune collision is unlikely due to their orbital resonance, the chaotic nature of Pluto's orbit leaves room for unexpected changes over extremely long periods. Even a slight gravitational perturbation caused by another celestial body, such as a passing star or a rogue planet, could alter Pluto's trajectory enough to disrupt the delicate balance that prevents a collision with Neptune. Additionally, as our understanding of space improves, scientists are discovering more about the gravitational influences of objects beyond Neptune, such as the hypothetical Planet 9. This yet-to-be-confirmed planet, believed to be much larger than Earth, could exert enough gravitational pull to influence the orbits of distant objects like Pluto. If Planet 9 exists, its gravitational effects could potentially increase the likelihood of orbital disruptions in the outer solar system. The role of Planet 9. Planet 9, if real, is thought to orbit the Sun far beyond Neptune, with a mass estimated to be 5 to 10 times that of Earth. Its presence could help explain the unusual clustering of orbits observed in distant objects within the Kuiper Belt, a region of icy bodies beyond Neptune's orbit where Pluto resides. Although no direct evidence of Planet 9 has been found, simulations suggest that its gravitational field could gradually alter the orbits of Kuiper Belt objects, including Pluto. If Planet 9's gravitational influence were strong enough, it might gradually shift Pluto's orbit closer to Neptune's, increasing the risk of a future collision. However, current models indicate that such changes would take millions of years, making any potential collision an event far beyond the time frame of human existence. Still, the possibility underscores the importance of continued research into the outer solar system and the forces that shape its dynamics. Could a Pluto-Neptune collision affect Earth? Even though Pluto and Neptune are billions of kilometers away from Earth, a collision between these two planets could still have indirect consequences for our planet. The impact would create an enormous explosion, releasing energy equivalent to billions of nuclear bombs. The debris ejected from the collision could be propelled into space, potentially forming a new asteroid belt or scattering fragments that might eventually reach the inner solar system. If any of these fragments were large enough and traveled on a trajectory toward Earth, they could pose a significant threat. However, the likelihood of debris reaching Earth is relatively low, as most fragments would remain in the outer solar system or be captured by the gravitational fields of other planets. Still, the potential for long-term effects, such as altering the gravitational balance of the solar system, cannot be entirely ruled out. The importance of continued observation. Given the complexities of gravitational interactions and the unpredictable nature of orbital dynamics, continuous monitoring of Pluto's orbit is essential. Advanced telescopes, space probes, and computer simulations allow scientists to refine their models and improve predictions of future celestial events. Missions like NASA's New Horizons, which provided the first close-up images of Pluto in 2015, have expanded our understanding of the dwarf planet's surface, atmosphere, and composition. Looking ahead, proposed missions to the outer solar system, including those aimed at exploring the Kuiper Belt and beyond, could provide even more insights into the forces shaping Pluto's orbit. By studying how gravitational interactions influence distant objects, scientists hope to gain a deeper understanding of the solar system's long-term evolution and the potential risks posed by orbital disruptions. Conclusion: the balance of chaos and order. Pluto's orbit serves as a reminder of the delicate balance between chaos and order that governs the solar system. While the gravitational interplay between Pluto, Neptune, and other planets helps maintain long-term stability, the system remains susceptible to unpredictable changes over vast timescales. The possibility of a future collision, though unlikely, highlights the importance of continued observation and research to better understand the complex forces that shape our cosmic neighborhood. As technology advances and our knowledge of the outer solar system deepens, scientists will be better equipped to predict and potentially mitigate any future threats. Until then, Pluto's orbit will continue to be a subject of fascination and study, a testament to the dynamic and ever-changing nature of the universe. Raising concerns about a potential collision, despite everything, between Neptune and Pluto, these complex forces try to prevent such an event from happening. Neil deGrasse Tyson, a prominent astrophysicist and a major contributor to Progress, offers an original point of view on our solar system's unsolved mysteries, especially the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides an enlightening analysis of the changing nature of space mechanics and the public's interest in the overlooked regions of space. Tyson's position on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He doesn't see the renaming as a reduction, but as a necessary adaptation to our growing understanding of the various objects that orbit our sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He sees orbital complexities like Pluto's as a sign of how much there is still to discover in space. The interest in these questions keeps the study of space so exciting. Despite Tyson's optimism regarding Pluto, a picture of a possible collision with Neptune presents a different perspective. His concerns about Pluto's orbital fate suggest that we may still have some mysteries to uncover. Will Pluto crash into Neptune? Or is this just another instance of miscommunication in the ever-changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial events with the intention of uncovering more of the secrets that lie far beyond our reach. Another question brought up by the potential Neptune collision concerns the mysterious and captivating universe in which we exist. The possibility of a mishap between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges our traditional comprehension of planetary stability. The idea that two celestial bodies with such a wide range of characteristics could collide is both frightening and fascinating, particularly in light of their current orbital strength. given that Pluto is situated in the solar system's outermost regions, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field. The implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To comprehend the dynamics of such a potential consequence, one must first consider the structure and properties of Pluto and Neptune. Despite being a dwarf planet, Pluto contains a wide range of substances and elements believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is coated with nitrogen ice, and its atmosphere is composed mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a vast gas planet, is mostly made of hydrogen, helium, and other lighter elements, with an atmospheric depth and density that distinguish it from terrestrial planets. A collision between these dispersed bodies would dramatically affect their structure and behavior, potentially creating an event noticeable across vast cosmic distances. What causes the hypothetical collision? The impact of other planets and bodies in the solar system plays a significant role. Despite Neptune's gravitational dominance in maintaining Pluto's orbital stability, it's just one of many factors at play. Jupiter, the solar system's largest planet, is another crucial factor. Jupiter's enormous mass and strong gravitational influence help stabilize Pluto's orbit, preventing it from wandering too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a devastating collision between Pluto and Neptune unlikely. However, despite the evident dangers, ongoing research has shown that the relationship between Pluto and Neptune is not as simple as a clear collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes, Neptune completes 3 orbits around the Sun, creates a kind of celestial lock that prevents them from coming into direct contact. This resonance is a key reason why the orbits of Pluto and Neptune, despite intersecting across the vast expanse of space, have never resulted in a collision. Although the gravitational influences of Neptune, Jupiter, and Saturn provide predetermined stability, the possibility of a catastrophic collision between Pluto and Neptune remains a subject of great fascination among astrophysicists. To truly understand the larger implications of such an event, it is crucial to delve deeper into the forces at play. One key factor is the concept of orbital resonances. This occurs when 2 or more orbiting bodies exert regular, periodic gravitational effects on each other, maintaining a stable configuration over long periods. In the case of Pluto and Neptune, their resonance ensures that, even though their orbits intersect, the 2 bodies can never collide because they are locked in a pattern that maintains a safe distance. This gravitational dance is a remarkable example of how celestial harmony can be maintained within the chaotic environment of space. The importance of this mechanism cannot be overstated, especially when considering the complex interactions between various planets and moons, particularly in the outer solar system, where distances and gravitational forces are vast and varied. However, the future of this delicate balance is not set in stone. The outer solar system is an active region with the potential for modifications occurring over long periods. Tiny, gradual adjustments to the positions or velocities of these celestial bodies could eventually disrupt the resonance, potentially leading to unpredictable repercussions. Such a shift could be caused by an external force, such as the gravitational influence of an undiscovered planet or a passing star, or by an internal event, like the gradual decay of orbits due to tidal forces. Continued observation and study of Pluto, Neptune, and other bodies in the outer solar system are essential for understanding the long-term stability of this system. As technology advances and new tools are developed to observe the solar system's farthest reaches, scientists will be able to refine their models and gain a clearer picture of the interactions between these distant objects. With new data, we may uncover more about the delicate balance that prevents Pluto from colliding with Neptune, or perhaps discover new forces at play that could alter their entire relationship.